So we got an example here of Newton's third law that's a little bit more complicated, and it probably is a homework question. So block A, let's give a description of this. We have block A that's tethered to a wall on the right, and block B is under it, and we're pulling on it with a force of 20 newtons. And blocks A and B, so block A has a mass of 1 kg, kilograms. Block B has a mass of 2 kilograms, 2 kg, and there's even friction. Even friction here between block A and B, friction between the B and the floor. So there's several different things we can do. You might try an interacting object diagram. Those interacting object diagrams, you know, are the things in the beginning of the chapter 7 where you've got the circles and all the objects, and that would actually be helpful. Maybe we can do that real quick. What are all the objects that are going on in this, well, in this picture? We got several things. We have the entire Earth. We have the surface at the bottom here. We have the wall, because the wall is, or the rope right here. And we have this agent, some sort of agent doing this pushing here. So it's a pretty confusing interacting object diagram. In the first chapter 7 video on the Traverso playlist, you'll find a simple one. Let's do a more difficult one here. So we got A and B. They're exerting forces on one another. I'm not going to have room. I'm going to have a bigger space here. So yeah, so we got A and B. They're more or less on top of each other. A is attached to the wall. B, and then you got the surface. The point of these is to draw the free body diagram accurately, but these can be problems in and of themselves. What else? And then we also have like an agent. Let's say that's the person applying the push. Okay. So when drawing this diagram, make sure to label everything. I'll do that down here. W is the wall. P is the external agent, whatever that is, doing the push. Pull. S, as always, is the surface. Double E, as always, is the entire Earth. And then A and B are just the blocks. Okay. If you're reading this, if you're watching this, or if you're paying attention and you don't know what we're talking about with these interacting object diagrams, do your best to follow along. So we've got, because the point of these diagrams is to show how these different objects interact with one another. Right? So how does the wall interact with A? It does so via the tension force. There's a tension between the wall and the A. How does A interact with B? This is what's tricky, is that A and B both, well, there's a contact force. So we're going to call that little n. But there's also a friction force, because if it's a rough surface, then yeah, then as B is sliding to the right, A is pushing it backwards. But B is also pushing it forward, which is going to give the rope attached to the wall tension in the string. And so there also is a friction between them, a kinetic friction force. Block and the surface have the same thing, a normal force and a friction force. Okay, what do these lines represent? They represent the forces between the objects. You know, the big conceptual takeaway is that, oh, forgot, oh, I drew the person at the wrong spot. I need to fix that. Oh wait, I can just select and drag it. Near B right here. Okay. I lost my train of thought when I saw the error. Yeah, so the surface applies a normal force and a friction force to B, but it's not exerting any force on A, or is it in contact with the wall or anything like that? I mean, the corner, but who cares? So then the block B and P have a force P with them. And then finally, the last one is, yeah, this is a really good example. I've never done this before, actually. There's a gravitate, so the entire Earth interacts with both the block B, so that would be like M sub BG. And then finally, if you've got the energy to draw this last one, it'd be A all the way down. It doesn't matter if these lines are straight or not, but we just need to know. Yeah. Okay. So that's an well, the last thing that this interacting object diagram is missing is the system. And I'm going to bold, going to increase the weight of the pen here so that we can clearly identify the system versus the environment. Now I might write on some of these other letters that I've drawn, but oh no, that works. Okay. Sorry, I only saw the bottom part of that. I know I'm drawing on the normal and the friction, but right. Okay. And so the box is what we represent as the system. Will this help for every free body diagram or Newton's third law problem that you do? Oops. My guess is no. It's a very useful tool when you're starting out. So when you're starting out, first learning how to draw all these things, all these diagrams, these are helpful. So that's the system. And then everything else is the environment. The wall is the environment, the whatever the agent is pulling on the block, probably some like hand yanking on it from the string. What else? The surface and the earth, those are external. And yeah, so this is a good interacting object diagram. Now let's continue and draw the free body diagrams. What would be the best way to do that? I'm saving this JPEG, but I'm gonna get rid of all the interacting object stuff. I think the best way to do it might just be to redraw the setup. So again, the setup is that we've got 1 kilogram block A, 2 kilogram block B, coefficient of kinetic friction between the blocks and the surface and B, that's actually defined to be both 0.2. And then we got a push here of 20 newtons. So there's technically two unknowns in this problem. One is the acceleration of B, because you can assume that the tension in A is enough to where it doesn't crack, but that is also a thing that's unknown. The tension right here from the wall. Okay, so those are the two unknowns in this case. Now, technically, with the interacting object diagram, we can draw a free body diagram. Oh, I see. Okay. Right. So let's draw the free body diagrams kind of near the relative to each other, and then we'll sum the forces. Trying to think if we'll have enough room below. I mean, these are very detailed, so I think the more space we have, the better. So I'm just going to draw one on top of the other. So this would be block A. This would be block B. Yeah, we might even have enough room at the bottom to, yeah, well, okay, and we'll sum the forces on the lower left-hand corner. So yeah, technically the interacting object diagram would be the thing that you would calculate to, or the thing that you would use. If you have that on hand, good. If not, okay. What's all the forces on A? Okay, well, A is not moving, so we have, the first thing is that we have F net of A equals 0. Several different things to keep in mind here. I am being explicit about A, cap A versus cap B. And we know that F net of B points to the right. I'm trying to stick with the notation of the textbook as much as I can as well. For good reason. I mean, they designed this notation to be very, very detailed, you know, for folks that are engineering majors, that they need that level of detail, especially in their later classes. So forces on A. If you go back and look at that interacting object diagram, you had 2 connections to B, 1 to the wall, and 1 down to the entire earth. So that means there should be 4 forces on A. So the first one, as we all know, is gravity. And here's where some people get tricked up. There is a normal force upward. But the new thing, so what is this though? What is the agent exerting this normal force? B. So this is N of B on A. And once you have one object in a system exerting a force on another object in the system, that activates Newton's third law. I tried to snap, but near the microphone, that didn't work out well. So since it, oh shoot, I'm drawing on the wrong one. I'm so apologize. Sorry, I got my magnifier on and I wasn't looking where I was going. Let me start that over. M sub AG, and then N sub BA. Okay, yeah, that's better. So that's going to activate Newton's third law. What do I mean by activate Newton's third law? Well, once you know that B exerts 1 on A, then you have to bring this vector down. And from my experience, you're going to want a lot of space on this left-hand side. So just bring it down like that. So that'd be the normal force of A on B. What other forces are acting on the block A? Well, there's a backwards tension. These arrows don't seem to be very good. There we go. Tension, an unknown tension vector matched by a friction vector. Okay. Now, a couple remarks. It's kinetic friction. It's not static friction. Some of you may be thinking, well, why is it kinetic friction and not static friction? Because the block's not moving. What affects kinetic or static friction isn't not necessarily the motion of the object, it's the motion of the object relative to a surface, even if that surface may be moving. So the A is moving relative to B, and so there is a sliding. Now there's another example similar to this one where you have B and A is on top and you're moving A like this and there's no rope. Well, in that case, the friction here would be a static friction force pushing A forward, you know, from this push or whatever, if it wasn't attached to the edge, because they would both be moving as one. And you've seen all this before when you got to push stacks of boxes. I mean, always have folks sometimes at work at warehouses stuff. I mean, and then another important point is that this is again B on A. So once again, that's going to activate Newton's third law. And so it's going to be a second action-reaction pair that you bring down and then write. F sub K of A on B. So you can see now why we wanted plenty of space. And so that's it for A. Questions, comments on free body diagram for A. And the good thing is that when you do the one for A, you pretty much start the one for B because you've got all the action-reaction pairs. So now you only need to think about all the external forces that act on B. And if you were to pull up the interacting object diagram for B, you would see that it's tethered to the hand or whatever. It's tethered to A. Tethered to A by the normal and the friction. Yeah, right, normal and the friction. But it's also tethered to the surface by a big normal and a big friction. And also being, of course, on the Earth with force mg. Right, and so if you look at this section of the interacting object diagram, you see that it's tethered to 6 things. There's 6 lines to which B is tethered. So that means there should be 6 forces on the diagram. Right, this is an example where, you know, there's lots of forces here. I'll erase all this stuff to go back. Fortunately, the clipboard goes back very far. So yeah, the gravity is obviously the one you want to first keep in mind. I'm just going to use m sub b times g, and then normal force. Now this is like a big normal force. Capital N. A friction force. Sorry, I'm thinking whether or not I should redraw this stuff. I guess I don't have to. I guess I can just, I can just move it. Yeah, that'd be easier. I'm someone who's very I get very particular about making sure my diagrams look right because, well, probably more than I need to worry about. That closer, get that thing closer. Yeah, and then the final force, well, we got 2 more forces in the horizontal direction. Oops, wrong bar. We have a backwards friction force. That is from the big normal force. We got cap F sub K, and then finally all that is matched out by the push or the pull. So you can see, like I said, why the free body diagrams in chapter 7 are so hard, and that's why we really were building up to them in chapters 5 and 6. Chapters 5 and 6, we had a lot of different ones, and I really hope when you did the problems that chapter 6 that you really worked through the diagrams. The ones I'm thinking of are ones where you have like a block sliding down a rough incline or something, or there was one where the block was falling on a rough wall and you had to apply a force to, you know, keep it from falling. Those free body diagrams are all fantastic practice for these harder ones. So after all that's said and done, what is the point of drawing the free body diagram but to get the equations? And I'm going to also move it a little bit so I have more room. In just a minute. Get rid of the A, get rid of the B. I'm going to try and circle all of this and move all of it, nudge it. Yeah, nudge it to the right a little bit so we have more room. Yeah, now we should have plenty of room to write. Good. So there's four, oops, I almost got, okay, I missed the N. If there's anything else that I missed, just let me know. It looks like the N is the only thing I missed. That's fine. Wait, what? Oh, okay, well, I'm not sure what that is now. Let's double check to make sure everything looks good. I don't know what that was now. It wasn't the Y. Okay. Oh, no. Oh, no. Oh, gee. Okay. I see. It was the newtons. Okay. It was the newtons, 20 newtons. Oh, I see what happened. All right. Select. Okay. Moving on. So let's sum the forces here. And I'm going to write four equations. Yeah. Okay. We got plenty of room. I'm going to write four equations. 1x, 1y, 2x, and 2y. These represent, probably clearly enough, represent the sums of the forces in each of the directions for each of the blocks. I even think there's a homework question where you have 3 blocks, but 2 of the blocks are only moving, there's only forces in one direction, so I don't think you ever have any more than 4 of these types of equations, but let me show you how complicated these can get. So let's practice summing these forces here with everything that we've got labeled correctly in the free body diagram. So let's do x. X might be the easy one to start off with. We got x equals t. So 1x, we've got, and this exercise by now should just be kind of artificial because you have the answer on the FBD, and so you're just writing it. Okay. Chat is a lot quieter today. Moving on, so we have plus t minus little f sub k equals 0. And we've got for 2x, technically you could really drop the subscripts, like this is technically n, technically this is plus n sub ba minus m sub a g equals 0. I think that I could be wrong. I suspect that the subscripts on the normal force, it would be safe to, well, it would be safe to delete them. Because you're just writing the n just now has the magnitude to it. And if you had like 5 or 6 blocks stacked on top of one another, then it might be a different problem. But anyway, so that is the ones for x, or for 1. The equations for b, oh, I guess whoops. This is ax, sorry, ay. I don't know if I'm going to make a b out of a 2. Okay. Sorry. That looks bad. Okay. So, jeez. Make sure, did I mess that up again? Oh, jeez. Okay. This isn't as bad as Wednesday, but let me just rewrite them. I wrote them in the wrong spot again. I'm sorry. So just give me like half a second. Okay, so we got those errors, but we wanted to make sure we got it right because the algebra gets kind of confusing later. So bx, that one's probably the harder one to do, but it's not impossible. By isn't hard. Usually we do by first, it's easier. So we have N, so plus capital N is the big normal force of the surface pushing on the block. That's going to be minus little n, which, okay, in this case it equals little mg, but minus m sub b g equals 0. If at any point you see an error, please stop me so don't go too far down the rabbit hole. And then finally, the A direction, we've got the big push or the big pull. So plus P minus 2 friction forces. F sub little fk from the A on B, and a big fk from B on the surface. And that equals, you might be tempted to say MA plus MB times acceleration, but it's still just plus M sub B times A. Okay, so questions, comments on this example, or on these sum in the forces. If you're still getting comfortable with this stuff, you might consider just using numbers. If you just use numbers, then the formulas will obviously look different. But the other, so this is 4 equations. And technically, we also know that friction, little friction, is equal to mu sub k times little normal, and big friction is equal to mu sub k times big normal. Yeah, so a very big system of linear equations. This is still linear equations, and so everything is linear. So if you know the mass, you could even plug this into a computer, and computer, you could even just solve it numerically, or not even numerically. You could solve it analytically. You could have some, if you have a computer that does like symbolic math or something, then you could even get that to work. I wouldn't get too fancy. Unless you're designing this for a company. Okay, let me move this a little bit. Let me nudge this a little bit more. Give myself a little bit more room. Oops, did I not move it? Okay, yeah, right. I just need a little bit more space. Yeah, we got plenty of space now. So I would, if this is your kind of first time solving one of these complicated problems, I would certainly use numbers and plug the stuff in. If these are 0.2, then you can calculate the friction forces pretty easily. N, so let's do some calculations, and then if people have thoughts, that we could try to do this symbolically. So little n is 1 kg times 9.8, so that's 9.8 newtons, which means little friction is 0.98 newtons. All right, no, 1.96 newtons, sorry. So this calculation is too hard once you get big N, then is technically it's equal to normal plus big mg, but you probably suspected that normal was equal to 3 kilograms times g. That's exactly what it is. So it's 29.4 newtons. That's 3 times 9.8, which is going to make big friction between surface and the block equal to 5.88. Yeah. All right. So N is 3G. Yeah, that's right. 3G, and then 0.2 of 3G is 5.88, so it's 0.6G, which is G 6G over 10. Yeah, right. 58.8 over 10. Good. Okay, so and then we got the 20 here. If the push is 20, then this X equation, becomes, this x equation, if you're trying to find acceleration, will become 20 plus 20 newtons minus 1.96 minus 5.88. 1.96 plus 5.88 is 6.84. Do I believe that, or is it 7.84 actually? Yeah, it's 7.84. So the sums of the frictions, it's 20 newtons minus 1.96 newtons minus 5.88 newtons. That equals plus 2a. Yeah, after all that's said and done, you end up with so 20 minus 7.84 is 13.08. 20 minus 7.84 is, no, it's 13.16, right? Yeah, because 20 minus 7 is 13. And
12.16.
Right. Meters per second squared. And then finally, no, the units are wrong. Kilogram meters per second squared. And then so finally, yeah, we're left with an acceleration of F net over 2. So divide that 12.16 by 2. I can do that. It's 6.08 meters per second squared. And that's the answer. Very good. So that's a pretty complicated example. The tension, that's easy. It's just 1.96 because it's just equal to friction. But the acceleration of the bottom block was a little more complicated because you had the two frictions. And those are the types of problems that perhaps a little bit more difficult on the front end. Technically, Newton's second law allows you to, third law allows you to do it more complicated. If people are interested, then by all means, go ahead and try to find the acceleration symbolically. The symbolic acceleration would be, and I can figure this out real quick. In terms of the masses, G and the push, M1, right. P, F sub K is mu M1G, big F sub K is mu M1 plus M2G. So factor out the, okay, right. If you can verify this, then good for you. It'd be P minus mu 2M1 plus 2, well, just say MA. Yeah, that's the answer in general. It better work if we plug all this stuff in. 20 minus 0.2 times 2, 1 plus 3G. Yeah, right. Okay, yeah, right. That's it. So this would be the answer in general if you feel like you want a challenge. And certainly not, this is, like I said, is a harder problem, but I certainly want to respect folks if they want to try and do some of these harder problems symbolically, because folks in physics 1, calc-based engineering physics are pretty smart. And so these sort of challenge problems, I think some of you folks will like that. So questions, comments on this more complicated example? Don't quite see anything in the chat. Thank you for that correction. 12.16 shows that there's some interaction out there in the Zoom void. Let's see. I will save this. I'll save this JPEG. I mean, it'll be recorded, but save the JPEG to study it. Get that stuff posted. Well, we have a few minutes. And really the problems, the other problems in this textbook, or sorry, the other problems in this chapter involve pulleys. The other problems involve pulleys, and so the important thing about pulleys, I probably won't do too many problems on this. We'll do more problems in next Tuesday, well, next time we meet, but basically here's a simple example with tension and a pulley. Sorry, yeah. The whole, basically the point is that the pulley acts as a force transfer of the tension. And so if you got block right here, you can go through the calculation of all the tension and the reaction-action pairs at every point to show that the force on the force of the wall, or sorry, the force of the rope on the wall is equal to mg. There's a systematic discussion of how that works. And well, the first thing is that on the block, you got T up, mg down, and those equal. Well, that means that the rope feels a downward force, which means on the top, it feels a force from the pulley. So this is the tension of the pulley on the rope, where this one right here is the tension of the block on the rope. This stuff isn't hard. It's just making sure you understand the terminology. But then the pulley acts to change the direction of the tension. So the bottom rope is feeling upward force. The pulley will make the top rope feel a rightward force. So this is also the tension of the pulley on the rope, which then does a second third law pair of the tension of the, this is the tension of the rope by the pulley. Oops. And then you work backwards. This is the tension of the wall on the rope. Make sure I got that right. Yeah, those are correct. Third law pairs, and then this one up here with the one down there matches the definition of tension. Right, and so the tensions and the pulleys act as a force transfer, and so you do problems like this, kind of like the one we just did, but involving pulleys, and that makes these examples a little bit more complicated. I think you're pretty thoroughly warmed up, but if we just do a quick one, this one's really so important, I might start on it on Tuesday, but if we got big M right here and then little m hanging down, this will actually show up for people in the physics lab on, well, I guess it depends, either this week or the next week, where you have the free body diagram for big block M is, the normal up and mg down, and then a tension that way. But then you work through all of that stuff to show that the same tension is pulling up on the little block. But one subtlety about this one is if you sum the forces for, let's see, for mx, it's what you would expect. It's just T equals plus m times a. Little my is actually plus T minus little mg, actually equals, if it's a smooth surface, it's actually an equal minus m times a, because it's accelerating downward. Whereas the block on the table is accelerating upward. And so the point is that you can imagine that you can add friction to this surface, or you can make it at an angle, or you could make it both of them be on surfaces. I think the most general type of one of these problems is something like this, where you got one block on one rough surface and it goes over, I think this is in the textbook actually, goes over and this is like a second angle 1 and 2, and seeing how, if it accelerates upward or downward, and then you can place limiting cases on it. It's a pretty helpful example that we might talk about next week. I'm not going to save this drawing though, but it's certainly another help. Okay.